Good afternoon. Welcome to the Embedded Executive Podcast. My name is Rich Nast. I am with Embedded Computing Design. This week's guest is actually pretty timely, and you'll understand that in a second. Frank Schurmeister, the Executive Director of Product Management for System Solutions at Synopsys, and an old buddy of mine. How you doing, Frank?
I'm doing really well. It's great to see you again, Rich.
Absolutely, absolutely. Although it is a podcast, so the audience is just hearing, not seeing. So
I
this
hear you
pink
too.
outfit that I'm wearing, nobody can actually see it. Anyway, so the timeliness I was referring to has to do with the Synopsys assist to ARM for the CPU that they just announced. Now, the background for the audience, we know ARM has been an IP company from its existence. I'm going to say it's like 30 years. I'm taking a guess at that, but I think they've been around for about 30 years. And they've never really done silicon before. And now they're coming out and doing silicon. And as I said, it was with a pretty big assist from Synopsys. So let me stop there and ask you, what did you guys do to help them?
Well, there's a lot of things going on in our partnership with ARM to enable external customers who use the ARM compute subsystems, our IP, and our tools. So there's in this 30-year timeline that you mentioned, there's a lot of work going on. We actually have a slide on that where I show over the last 30 years how their tools have developed, how their IP blocks have developed from cores to subsystems. Remember things like Big Little and Dynamic Q, and then now they have the Neoverse class subsystems where in parallel Synopsys IP has developed. So these subsystems need to connect to things like DDR, PCI Express, and in the world of chiplets to UCIe and others, the die-to-die interfaces. So we have been working with them, and obviously when they build chips, they will use the tools and the IP that we provide as well.
Well, if we get a little bit of a history lesson here for our older listeners, this was actually where the whole RISC thing started, if I remember right, because it was always CISC and Intel and x86 CISC, and all of a sudden we had this reduced instruction set, which now we know is far from reduced, but at the time it was a much smaller instruction set. But anyway, that sort of brings back a few memories for me. But anyway, let's get back to the present. So what was the assist from Synopsys in this hardware?
Well, the way to look at it is really Synopsys enabling ARM engineering teams to build this chip in record time, right? So it's really, really amazing to people with slightly more gray hair like you and me to...
Whoa, hang on. I don't have gray hair.
Oh, you don't?
Let's just clarify that for the audience who can't see us.
It must be just me then that there's like a little bit of sand in the snow in the mountains.
I have to change the filter on my camera so it doesn't look great. Anyway, sorry, go ahead.
So we assisted the engineering team in enabling them really to be as productive as they were to get out this chip in record time, right? So it's not only enabling the customers.
Would you quantify record time? And we don't have to talk specifics, but what's typical and what did they get that down to? And what did you do to help them get down to that number?
So I think they didn't quite disclose the full time for the chip, but it is that we are talking about the enablement of the subsystem from idea to silicon in really almost a year's time, which is like really, really fast given the yearly rhythms in which these chips are doing. And that three concrete items to make it quantifiable, because you're pinning me down on this, which is your job, are really like the enablement from an IP perspective. So ARM's focusing on the compute subsystem. We are the leader in interface IP. So there is IP involved like PCI Gen 6, for example, which is connecting to the ARM compute subsystem to connect to the outside world. The second bit is really a suite of EDA tools, all the way from verification all the way down to IC validator. That's how my boss's boss always refers to it about this. So it's the flow top to bottom, if you will, all the way to sign up to then going into an advanced foundry node. And the third thing is something which has become a really, really important, critical, and market that you really can't live without to get these chips out, which is the hardware assisted verification domain. So that includes things like the ZeBu emulation system, and we also have HAPS for FPGA-based prototyping there, which is really allowing you to get the shift left, as the industry calls it, as a buzzword, in a way that you can run AI workloads, so the items that the ARM AGI chip enables, before you actually have the silicon, right? So you move this into a pre-silicon phase, running real AI workloads. 10 years ago in mobile phones, it was running Angry Bird and before things like that, before you actually run and tape out a mobile chip. For these data center compute chips, it's all about running AI workloads prior to silicon. And you do that with
But
hardware assisted verification.
what you're describing sounds like the process you would use with any ASIC customer. Was working with ARM different from any other customer?
It's essentially the same semiconductor full flow that many other customers are using, right? If you look at ARM's evolution, and Rene pointed this very nicely out in his keynote when they announced this in the middle of March, they essentially are having IP, they have subsystems, and now they have done silicon that they sell. So they have to apply the same techniques that semiconductor developers have been doing, from the early architecture through the software enablement, through verification at various stages, coming from just the interfaces. They have cache coherent interfaces on there that need to be verified. You have verification IP for this. Then you drive it into things like ZeBu for bringing up the connections to things like PCI Express prior to silicon, so that you can really do, I think ARM refers to soak testing, that you can really run very large number of workloads, including AI workloads, through the design before you actually then commit with confidence to get it into the advanced technology nodes.
Is if I'm a board designer or a system designer, do I need to interact with Synopsys, or is your job done and I just deal with ARM at this point?
I'm not sure that I understand that question in full. As a board designer, you, for the chip, use the specs ARM gives you for the chip and you integrate it. There's in this day and age, as we have reached a point where the chips are getting as big as reticle limits, so you have yield questions to work through, so you switch to chiplets. When it comes to that, you interact really with providers of those chiplets, but then also with us as Synopsys, providing you the verification IP, providing the connection pieces in what we call modular hardware-assisted verification, where the verification setups now mimic essentially those advanced multi-die designs. So think about a compute portion that you get from ARM, and now you want to integrate that with your own AI accelerator, right? We actually have a couple of really good examples. I had the privilege to present at ARM's Total Design Summit a couple of months back worldwide, about how the customers, or for both of us, integrate their AI accelerators with the ARM subsystem. So that's not the full chip they use here, it's really the subsystem. Then they use basically the licensed portion, put it on a chiplet and run it with their chiplet. That all is done using our tools. So they interact both with ARM for the content. They add their own content to it. So a great example, which we really enjoy using, and it's very public, we have talked about this many times, is a company called Rebellions, out of Korea, who has essentially their AI accelerator. They map that AI accelerator into something like ZeBu emulation. So now you have a very accurate, high fidelity, and fast representation. So this runs in the area of multiple megahertz before silicon is even available. And now you run your AI workloads on a, let's say, a Llama LLM that you run on a Linux, and that's all operating on top of the ARM compute that runs on a host. And you have with that setup then the ability to optimize the performance, for instance, of the interaction between the compute subsystem and an AI accelerator. So customers will always interact with both ARM and us as Synopsys as the enabler with the tools to put these together at kind of the board level. And the board level these days, which has basically become often chiplet integration at that, so that your design that used to be just homogeneously one big piece of silicon, the system on chip becomes a system of multiple chiplets, a multi-die design. And you want to verify that as much as anything before you commit to the advanced packaging to combine it all.
So, as much as you're allowed to share, walk me through the timeline of how Synopsys worked with ARM. When did it start? When did you first engage with them on this project?
Well, so the exact timeline we typically do not disclose. It's very similar to every semiconductor customer, where the interaction starts very early with the IP selection. And that's often done just based on specs, but then people use early on the architecture capabilities in tools we provide, like Platform Architect, where you do the assessment how your workload intensity, for lack of a better word, so the compute performance, the compute power of the workload is basically modeled on top of model representations at the architecture level. So that happens like 12, 18 months often before the silicon is available. That's a very early part of the chip development process. And then we talk about how you enable the software developers for your design very early on, so you get those pesky software developers off your back, so to speak, to do development on virtual models. And there's an interesting thing coming together. ARM, of course, for their compute subsystem has their own models. They call these fixed virtual platforms, which then are mapped into using our tools together with the models of the IP around it. Let's say things like a PCI, things like DDR, things like die-to-die, UCIe interfaces around the compute subsystem. You add the model of your AI accelerator around, and then you build a virtual prototype, as we call it, for the software developers. So now you are 9 to 12 months before silicon. And then we have already in our partnership with ARM, which extends even into the standardization committees, if you will, we have already verified that our verification IP, for instance, works well and can be used by users to assess how a CMN cache coherent interconnect as I needed, how that's all verified. And then you have tools, you run very large workloads to really look at those coherency items, to validate all that within the compute subsystem. ARM does that, and then in coordination with the AI accelerator around it. So now you are 6 to 9 months pre-silicon, right? And at one point you come to the phase where you run functional verification, you run hardware-assisted verification, you bring up these prototypes now in a high fidelity version of the prototype, which is a ZeBu emulation. You even do things like the standardization and compliance well before silicon these days. ARM has these system ready compliance suite. So there's we can call it SBSA in the server world, compliance, which basically is a set of tests that say if you run these tests correctly, then it will work for the OEM integration later on. And you run these pre-silicon on things like ZeBu emulation, and then you bring in the software as a partner we often refer to as well, AMI, for bringing up essentially the BIOS and so forth well before silicon. Now you are 3 to 6 months before silicon. At one point, you have to commit to all the digital implementation pieces based on the technology you have. So you come to the point before the tape out where you can only do ECOs. But functional verification and bringing up software, booting Linuxes, running AI workloads, pre-silicon, all continues in full swing. And then you tape out the chip, you get it back depending on your agreement with the foundry. What is it, 12 to 18 months, 12 to 18 weeks, something like that. And the idea of doing all this pre-silicon shifting left, so shifting left into the hardware-assisted verification engines, and then even shifting lefter, which you have done earliest into pure virtual engines. The result of all that is that when the silicon comes back, the software comes up in amazingly fast time. So we had companies like Rebellions who they are using essentially the ARM integration there, how they were coming from silicon to customer demos in a couple of weeks. So they talked at supercomputing conference and at our Snugs about that. So it's very, very fast for the software to come up because you have done all these pre-integration tasks, shifting left and do all that validation already pre-silicon.
That is awesome. So it sounds like everything, for the most part, went according to plan.
Absolutely, absolutely. Yeah, and congrats to the ARM team. Amazing job. We are an enabler in all this. We are a partner with the IP, as mentioned, enabling them with the right tools. Well, and of course, there's the occasional call. There, management calls on one side. Hey, this we need your attention on this. All hands on deck, and that happens like in every project. Even if you build your house, you will have conversations with your GC. That the water was switched off too early or too late, whatever. So you have all these things happening in the context of chip development as well. And it was a great partnership. Congrats to the ARM team. And we're very proud having been one of the prime enablers of the tools around it, the IP as mentioned, and the top to bottom architecture to implementation. Usage of the tools.
And congrats to Synopsys as well. Job well done.
Thank you.
Thank you, Frank. Thank you for walking me through that. That makes it very clear to me.
Excellent. Glad to talk to you again. We both were more embedded guys when I had darker hair. You of course haven't changed, but
Well,
it's amazing
thank you for
to
setting
see
everybody
all this.
straight.
And exactly, and to see the embedded software there is interesting because we have talked about that really years ago already. How you bring the hardware software interface together so early, and that's a very critical part of the whole shift left activities.
Absolutely. That was Frank Schurmeister. He is the Executive Director of Product Management for System Solutions at Synopsys, and I am Rich Nass with Embedded Computing Design.
Thanks for having me.